Analyze and sketch a graph of the following function. Label any intercepts, relative extrema, points of inflection, and asymptotes. This information, intercepts, relative extrema, points of inflection, and asymptotes, tells us all that we need to know, all that we need to compute and look for. So we have a function f of x equals x cubed plus 3x squared minus 9x minus 27. The first thing I'm going to do is go through and find the intercepts, and the first type of intercept I want to find are the x intercepts. That happens when f of x is 0. So when you set f of x equal to 0, and the rest of the equation can be solved for x, I see that this can be done by grouping. So I can common factor an x squared out of the first two and be left with an x plus 3. I can common factor a negative 9 out of the last two and be left with an x plus 3. Oh, awesome. This is going to work out really well. There's an x plus 3 and an x plus 3 in common, so I'm going to factor that out. X plus 3. And then what's left, this x squared minus 9, will be right here. And it turns out that you can factor this into x plus 3, and the x squared minus 9 can be factored into x plus 3, x minus 3. Thus leaving you with the x plus 3 squared times x minus 3. And all of that is equal to 0. So when you set each of these factors equal to 0 and solve for x, that tells you that x will equal positive 3 and negative 3. So we will have two x-intercepts. To find the y-intercepts, that is when you let x be 0. Y-intercept happens at x equals 0. So what that means, just by substituting 0 into all of these terms here, they all go away, and we're left with a negative 27 for the y-intercept. And while we're on it, since I just have a little bit of space left on this page, the asymptotes for this graph, this is a polynomial graph. There's nothing rational about this polynomial or about this function, so there are no asymptotes for this function. On this page, the goal is to find the relative extrema and the points of inflection. So in order to find the relative extrema, we need critical values for this function. In order to find critical values, we need to take the derivative, which will be 3x squared plus 6x minus 9, which is the same thing as 3 times x squared plus 2x minus 3. In order to find the critical values, we will set that equal to 0 and solve for x. And I know that I can divide both sides by 3 here to get rid of that 3. And at the same time, I'm going to factor this. So I will be left with x plus 3 times x minus 1 equals 0. And from here, I can set each of these factors equal to 0, and I will get that the critical values are x equals negative 3 and positive 1. From here, I could use the first derivative test to see whether or not these are relative max or relative min, but I'm going to go ahead and find the second derivative now and find the points of inflection and use the second derivative to check whether or not these are relative extrema. So from the first derivative, you can find the second derivative by the power rule. That gives you 6x plus 6. And to find any possible points of inflection, we can set this 6x plus 6 equal to 0 and solve for x, and that tells you x equals -1. So to find a point of inflection, we definitely have to use a number chart or a sign chart here. So at -1, I've got this. I need to test to the left of it. I'm going to pick -2. And you evaluate that in the second derivative. And over here, I'm going to pick 0 and evaluate that in the second derivative as well. It turns out that if you substitute -2 back into the second derivative, you will get an answer that is negative or less than 0. So to the left of -1, this is concave down. And if you go back to the second derivative and you substitute in 0 here, it turns out you'll get something positive, and that means it's concave up. And since the concavity changes at this x value, and that this is not a discontinuity, then there's a point of inflection at x equals -1. And we can actually get very specific with this by taking this x value and substituting it back into the original function to get an ordered pair of -1, -16. So here is the point of inflection. To tell whether the critical values are relative max or relative min, I'm going to use the second derivative test. The second derivative test states that if you evaluate the second derivative at a critical value and you get something that is negative, let's see, this is f double prime of -3 equals 6 times -3 plus 6, which is -12, which is negative, and you get something negative, then you have a relative maximum at that x value. And if you substitute in a critical value, say 1, and you get something back that is positive, then you have a relative minimum at that x value. And that's because when the second derivative is less than 0, that means it's concave down, which means it should have a maximum in it. And if you have the second derivative being positive at a particular point, that means it is concave up. And if it's concave up, it looks something like this, and we'll have a minimum value. And in fact, since we know what the original function is, right here, f of x equals x cubed plus 3x squared minus 9x minus 27, again, we can get very specific with these x values in knowing exactly where they happen. On this final page, I have listed over here on the left all of the pertinent information that was found on the previous pages, plus a little bit extra here with this concavity. It wasn't necessary to find the intervals of concavity, but I figure it couldn't hurt to have it for sketching our graph. So over here on the graph, I'm going to put all of the pertinent information on this graph. There is a relative maximum at -3, 0, so maybe like right there. We'll call this 1, 2, 3, -3, 0. It means the graph will top out here, so it looks like it's going to do something like this. And over here at 1, -32, something about right here. There's negative 32, there's 1. There is a relative minimum, which means it's going to bottom out right there. Let's see what's next. The point of inflection is at negative 1, negative 16, so maybe about right here. That point, negative 1, comma, negative 16. And while I'm at it, let me label this point. This is 1, comma, negative 32. The last couple things we need to label, the X Intercepts. There's already an X Intercept here at negative 3. The other X Intercept happens over here at positive 3. So I'm going to put a dot there, and I'm going to call this 3, 0. And then the very last point we need to put on the graph is the y-intercept at negative 27, maybe about right there. So this ordered pair is 0, negative 27. So I guess we just get to connect the dots from left to right here. So I'm going to start here, go down the point of inflection, go through the y-intercept, come straight up here like this. And then the left side of the graph is going to do something like that. There's the sketch of your graph. Let's double check really quickly. To the left of this point, this graph looks pretty concave down. To the right of this point, this graph looks pretty concave up. Yeah, there's a sketch of your graph.